Hello and a very warm welcome to you. Today I'm posting a short video about the Coriolis Effect or Coriolis force. Now I'm a little nervous about doing this because I'm not a physicist. I'm a humble biologist and I stopped studying physics at high school. So my understanding of physics is high school level plus any bits and pieces that I've picked up over the years. The main reason for posting this video is to confirm that I've got things right, that I'm understanding a situation correctly. And the second reason for posting it is because this has been the subject of some discussion on Jose JG Gonzalez's channel over the last few days, with flat earthers making various claims about the Coriolis effect not being present at all, or somehow disproving the spherical Earth model. So I want to address the questions that I've heard asked and see if I've got things right, and perhaps provide a little bit more insight for the flat earthers who are asking these questions. So the conversations that I've heard, the flat earthers have been asking us to consider a flight going north to south on a rotating spherical Earth. So here is a representation of the spherical Earth, and I've decided to consider that as an extreme case of a plane taking off from the North Pole towards a landing site on the equator. Now, before we actually consider that particular case, I want to consider another hypothetical situation. That is a helicopter hovering above the North Pole, firing a projectile towards a target that's on the equator. So here we've got a helicopter hovering above the North Pole. You need to sort of imagine it facing straight towards you and straight towards the target here. Viewed from the reference frame of the helicopter itself, a projectile, and it's a projectile, it has no means of steering or propulsion. Its propulsion comes from the firing, and at that point it has no additional input in terms of propulsion or direction. The target moves into the location that we're going to start the process and fire the projectile. The target is obviously still moving, and the projectile will, from our point of view on the helicopter, fly in a straight path towards the point that the target was located when we fired it. But of course, the target has moved due to the rotation of the Earth. Now, I'm ignoring any effect that the atmosphere might have, whether that be the atmosphere moving en masse with the rotation of the Earth, or winds moving in different directions as the projectile flies. So really considering this in a sort of zero atmosphere or zero atmospheric input situation. Now, if we view from the rotating reference frame of the Earth, so from directly behind the target, the projectile will appear to deviate to our left. Not because the projectile has deviated, but because we are moving to the right. Again, ignoring the any effect the atmosphere might have. Now if we view from a reference frame of a second helicopter hovering just beyond the target. So we have the target in our view and the helicopter that fired it in our view. The projectile will appear to fly straight towards us, but will miss the target because the target moves to the right. So your location and your reference frame make an enormous difference to what you actually observe, and I think it's important that for people asking questions about this to kind of understand that. Now, I have tremendous difficulty understanding reference frames. It's not something that I've spent a lot of time trying to get my head around. Hopefully I've got that kind of right. So I don't know why the arrow did that. So let's go back to our situation of our hypothetical flight from the North Pole. The moment of takeoff, so its wheels are just on the ground, the plane has zero tangential velocity, assuming that the takeoff point is sort of bang on the North Pole. It's a hypothetical situation. Its nose will be pointing directly at the target landing site at this point, until the moment that the wheels leave the runway. So the moment that the wheels leave the runway, the direction that the plane is pointing will start to become slightly different to the location of the target. Let's just hold that moment in our head. Okay, the plane has just taken off. The target landing site is moving away in eastward direction. So as we're looking at it, to the left. Once airborne, the plane is flying through air, and that air is also moving and rotating with the Earth. Now, because the target is moving to the left with respect to the direction that the nose was pointing at the moment that the plane took off, if you imagine observing this from a helicopter hovering above the pole, as we spoke about before, the plane must deviate from a straight path from that helicopter's point of view. So that helicopter is looking straight towards where the target landing site was, and it will see the plane start to veer to the left as and see the target move to the left. But if we're viewing that same flight from the target, then the plane will appear to fly in a straight path directly towards us. So that's the direction that the landing site is travelling, and the arrow indicates the direction that the plane must adjust its flight. Now, the questions that are being posed by flat earthers, or one question that's being posed, is how does the plane maintain its course directly towards the landing site from the perspective, from the reference frame of the landing site? Because if it doesn't make any adjustment, if it doesn't deviate at all, then it will do what the projectile from the helicopter did, and it will miss the landing site. Now, from what I've heard, two answers have been given. One answer is that the air is rotating along with the Earth and imparts a force on the plane, and enough force on the plane that it follows the required flight path. The analogy here might be an object perhaps that is fixed, held in place in a flow of air or liquid fluid of some sort. The moment you release that object, it's carried along with the flow of that fluid. The second answer that they've been given is that the pilot or the autopilot makes small steering corrections throughout the flight to maintain the required flight path. Now, for me, the question is, which of these two answers is correct, or is there something else going on? So, answer one, is it true that the air is rotating along with the Earth? Well, yes, it is. En masse, the atmosphere rotates along with the Earth. However, it's also true that locally, where the plane actually is, it will experience winds of various directions that will either increase or decrease that apparent rotational speed as far as the aircraft is concerned. And the pilot will need to adjust, obviously, for wind speeds. And I don't think anybody would disagree that the pilot needs to correct for wind. Anybody who's driven a car, for example, in a crosswind, or ridden a bicycle in a crosswind, will know just how much you have to correct for a crosswind. So because of this, it seems highly unlikely to me that the air alone, the movement of the air alone, can keep the plane on a flight path directly towards the landing site. But I do think that the rotation of the air might have some impact on keeping the plane on the flight path. The second answer is that the pilot makes corrections, and clearly the pilot, as I've just discussed, must make corrections via the plane's various steering mechanisms to maintain a direct flight path towards a landing site. I mean, they will come across crosswinds, and those crosswinds may well change in direction during the course of the flight. So sometimes from west to east, sometimes from east to west, and adjustments will need to be made in order to correct for those winds. Obviously, the type of wind, amount of wind that is encountered varies considerably depending on the altitude that the plane is flying at. So a plane flying at in excess of 10,000 meters will experience very different winds to a light aircraft that's flying at 3,000 meters or something of that sort. So most of the corrections, I think, will be made to compensate for local wind changes in wind speed. And these are going to be far greater than changes required to compensate for the fact that the target is moving away to the left. And it's also important to say that the pilot won't be thinking about making the changes, I'm getting blown at this amount to the east, so I need to correct by this amount to the west, or vice versa. The pilot will simply be trying to maintain a course heading directly towards the landing site, assuming that that's the flight path that they've chosen. So my answer is that I think it's a combination of both answers. I think the air movement will have an effect, and I think that the pilot will make course corrections, and that the combination of these two will allow the plane to maintain a course heading directly towards the target. And I see no problem with this. I don't understand why the flat earthers aren't able to simply accept that this is true. Now, a further question that's been posed is whether the air at cruising altitude of greater than 10,000 meters for an airliner has sufficient density to apply enough force to the plane to keep it on course towards the target on the equator that's rotating as well. Well, this seems a kind of irrelevant question, because the pilot is making corrections. So if the air at lower altitude is more dense and has a greater input than it does at high altitude, it really is unimportant, because the pilot will be making course corrections all the time and maintaining the heading required. And so it doesn't matter whether the input from the atmosphere varies with altitude, because the pilot will be able to compensate for that. And now we come to the last claim. This one particularly made by a flat earther called Chris Berry. I don't know whether others have made the same claim. And this is the suggestion that just before the plane lands, it must have accumulated an additional roughly 1670 kilometers an hour speed in order to match the rotation of the Earth. So obviously in the way that the question is phrased, it's gaining that speed all the time throughout the flight. It's not just suddenly gaining that speed at the point of landing, but by the time it lands, it must have picked up that much speed. And the claim is that that speed is in addition to the plane's airspeed in north-south direction, and that the total speed is much greater than the plane is capable of achieving. I think this question represents a misunderstanding of the concepts of speed and direction and reference frames. So the speed of the plane is measured by considering its movement relative to something else, and normally that it would be relative to the ground, relative to the air that it's flying through. Since the ground and the air en masse are both moving at the same speed of rotation, it really doesn't matter which one you choose. Yes, the movement of the air will be affected by wind, but we'll not worry about that. At no point in the flight does the plane's speed with relation to the ground or the air through which it's flying need to exceed its maximum possible speed. The plane is simply flying through the air at, say, 500 kilometers an hour, or no, it's probably more like 800 kilometers an hour, 500 miles an hour, if it's an airliner. And it's flying through the air at that speed. That's the speed that it likes to cruise at. The pilot chooses to make it cruise at. The pilot makes the adjustments as required to maintain the course of that plane towards the landing site. There is no increase in speed by the plane relative to the ground or the air that it's flying through. And asking how did the plane gain the extra 1670 kilometers per hour speed is pretty much the same as asking what does the color blue taste like. It's just a completely nonsensical question. The plane hasn't gained any speed at all relative to the ground or to the air that it's travelling through. Now, I've tried to find a simple way to explain this that Chris and others might understand. The best I've been able to do is this, so bear with me if it doesn't make sense, but I think the misconception that they're having is that the distance between the takeoff and landing spots on the Earth does not actually change throughout the flight. And the distance through the air between the takeoff and the landing spots doesn't change throughout the flight. So if the average flight speed is 800 kilometers an hour and the distance is simply that distance, then the average flight speed doesn't have to go up or down or change in any way. And I think Chris's misunderstanding comes from the idea that he might have that the plane is following a curved path instead of a straight path. So if you view it from, let's just go back, if you view it from the point of view of the landing site, looking back towards the plane is simply travelling a straight path. And that path length doesn't change. What Chris appears to be doing is considering it from a viewpoint of the second helicopter I referred to, just beyond the landing site at the moment the plane takes off, but remaining fixed in position. And now the plane has to travel this path indicated by the curly arrow, and obviously that's a much longer flight path, and so a plane travelling that sort of path would travel a much greater distance and therefore needs to travel faster in order to cover that distance in the same time. So I think Chris is mixing up his reference frames here when he asks that particular question, and the question simply doesn't make sense, because to consider it from that reference frame doesn't make any logical sense at all when you're considering the speed that the aircraft is travelling. So that's my, I'll happily admit it, rather simplistic take on the various discussions that have been going on. I will admit I haven't listened to all of them, and I dare say that many other people have done a much better job than I just have of explaining what's going on. But perhaps my rather simplistic high school level understanding might serve to help the flat earthers who are struggling with this to understand. As I said earlier, if I've got something horribly wrong, please tell me. I want to learn and get a better understanding of this. So thank you for watching, and I look forward to reading your comments.